Okay, hi everyone. So for this other topic, we want to now discuss the cases where the lump system analysis won't be applicable anymore. No. So if there are cases where the byte number is greater than zero point 0.1, then as you imagine, the temperature distribution will be much more apparent. So it is not uniform at all, the temperature within this body. And that complicates the problem because we have to consider the temperature gradient, no? Which affects the heat transfer, no? The heat conduction as well. So, um, okay. So for the sake of simplicity, what we can do now, we can imagine is that the Waller cylinder is exposed to a uniform environmental temperature with uniform coefficients as well. So one other assumption is that the temperature of the object initially is uniform initially. That is the TI. And also the coordinate system that we will be using is that the x coordinate, no, the origin of the x is in the center of the cross section of our body. So for a large plane wall, we have the center of the plane wall as our zero coordinate. So as you can see, the thickness will be 2L if the L is 1/2 of this from the center. No? Same goes for the cylinder. So we have the radius, and then for the sphere, you have another radius. Okay, so with this assumption, with this case, we can at most simplify this, but simplifying this is an understatement to how complicated to solve this problem using differential equations. Now, as you can imagine, if this is a scenario, as you can see, the temperature or the initial temperature is at this point. So let's say you have this initial temperature. So this is a high temperature, and then the temperature of your environment is at most this. So you have a hot body, and then you have a cool environment. So what happens if it is exposed in this low temperature environment? You have a high temperature body. As you can see, the temperature will be affected here, no? So the surface will cool down, but the temperature within the body won't really be affected at first. No? So as you can see, this is the T is equal to T1. This is just an approximate value for let's say a few seconds, a few minutes. And after a while, the temperature will get closer and closer to the, so it will be closer to the environmental temperature. So this will be the temperature profile. Then after that, the temperature of the body will be uniform, which is also the same as the temperature of the environment. So you can imagine the scenario, you have initial temperature, then after a while, the surface will be cooler, no? But the inside will still be hot. No? And then it will get colder, the inside will also get colder and colder, and then it will have the same temperature after a while, no, after t approaches infinity or the time approaches infinity. So we want to solve this phenomena, and we can use differential equations for that. And we know, no, initially that we have this heat conduction equation for transient conduction without heat generation. So this is the differential equation that represents this phenomena for transient conduction. To be specific, this is one dimension, no, transient conduction. So we're going from 0D into one dimension. No? So for one dimension, what when we do is we can provide our boundary and initial conditions. So basically, we have three conditions now. So we have two boundary conditions. We have one initial condition. So if you might recall, for differential equations, if you have an nth order differential equation, you would need an n number of conditions. So for this case, you have second order, no, and the first order here. So they have a different variable. That's why they are separate. Now you have a partial differential equation. So you would need two boundary conditions, and you need one initial condition. Okay, so that's it basically, no? So that's why we need two boundary condition and one initial condition to solve the differential equation. So you want to first solve the general solution, and then you can substitute the boundary conditions, and then you already have an equation that represents this phenomena, this heat transfer of this transient conduction in one dimension. So it is really hard to solve this, no, if you can imagine. And I guess I'll just explain this briefly, So this basically means this first boundary condition basically means that the slope, no, the temperature slope at the middle will always be 1, no? So I hope that makes sense, no? The tangent or the slope at this, no? So at x is equal to 0, meaning this is x is equal to 0, right? This axis right here. And anytime the slope of this will always be 0. No? That's basically the first boundary condition. The second boundary condition, this one, this basically means that the conduction and convection are equal at the surface. So we have L here because this is the coordinate of the surface, no? This is the axis of the surface. So the conduction and convection of the surface are equal. So convection removes heat, and then conduction will add heat, no, in somewhat way, no? Sorry, actually it should be this direction. So entering the node and then exiting the node. So, and then the initial condition basically means at all x's, no? So for all x values, so from 0 to L, no, actually in symmetric form. So all the values of x here, the temperature, the initial temperature when T is equal to 0, no? It is the initial temperature Ti. So the temperature of the body will always be a straight line for our assumption. Although you might have a different profile like this, but that will be a different problem, no? So we cannot solve that right now yet. Okay, so that is a more advanced way to do that is will not be discussed in this lecture. So it is really hard to solve this differential equation, and one way to really solve this is actually there is a technique, no, by this is inspired from the textbooks of Sengel and Incropera, wherein they non-dimensionalize the differential equation. No? So basically, they simplify this left part, no, and then made it like this right part. So basically, they just manipulated some of this to make things much more simple so that it is much more easier to solve. So I won't get into too much details, but here are also the computations, no, inspired again by the textbook on how it was non-dimensionalized. So the non-dimensionalization, well, to be simple, is that instead of having x as a variable, you have the ratio of x over the length. So that your range will vary from 0 to 1 instead of x or 0 to x or 0 to L. No? And the same goes for temperature. You can non-dimensionalize temperature. So instead of some temperature range, you have this, so that the range is from 0 to 1 again. Okay? So I won't discuss this too much, but you can see my notes here and where did everything came from. Oh. And then you can solve for, okay, you can solve for, sorry, it can be represented by this differential equation. Now you can solve this differential equation using variable separable. No? So usually we can assume that if the differential equation, well, the simplest one that we can solve is the variable separable. For partial differential equations, we can assume that we know that the solution is theta, no? The function of theta. Therefore, basically it's just they are independent of each other, no? So meaning they are factors, they're product of independent functions of x and tau. So the tau here is the Fourier number, which is equal to um, the thermal diffusivity times time over L squared. Anyways, after that, we have solved this, and you have this two partial different. Actually, this will be an ordinary differential equation at this point. you can solve this two differential equation into this form. Okay. So basically, this is a linear differential equation, right? Linear differential equation. So the solution form is this and this. If you multiply these two functions, since the general function is this. Sorry, I won't get into too much detail, but uh, you can solve this. Now, this is the general form of your solution. Now, if we substitute the boundary conditions and the initial conditions, what happens is we have a particular solution. So this will be your particular solution. And you can now solve for theta, which is this t minus t infinity minus over ti minus t infinity. So basically, you can find the temperature using theta. Okay, so theta is just the difference of temperatures, right? So after that, you have an answer basically. But the problem is before you can solve that, you need the coefficient a and the lambda. No? So the coefficient a is in some way uh, correlated with the lambda. And to add to that as well, the lambda, no, has an infinite solution for this one. So if you graph this, you can see that you have an infinite solution of the lambda here. No? So given your Bayes number, you can solve for lambda. After the lambda is given and the area is given, you can solve for the temperature. So the problem here is that it has infinite solutions. No? And if you have infinite solutions, you have to add that solutions to form the solution. Because in linear differential equations, no, I hope you remember this, it has an important property which is linear superposition. Differential equation is, sorry, you have a property that is linear superposition. So what that basically means is if you have one particular solution, you can add another particular solution to that, and you will have a general solution. Sorry, not a general solution, but you will still have another solution. So adding more solution will still be a solution, no? It's an interesting property for linear differential equations. And basically, it will form an infinite series since you have an infinite solution for lambda. And if you use the initial condition, the an will be equal to this. And then you can also basically your temperature in theta form using this value, no? But the problem is it is quite hard to evaluate this since we have an infinite series. So this is basically the exact solution of your heat transfer problem. So you have to first find the eigenvalues, no, the lambda. I didn't mention that, but the lambda is also called the eigenvalues. And then evaluate the infinite series. But there is an easy way around this. We can approximate the solution, no? Okay. I forgot to mention we also have the Bessel functions J. So you can evaluate the J value, no, J function using a lookup table. Also, it will be generally easier for us because the textbook already solved this for us. We just input, we just plug in the values and we're gonna have a solution ready. We don't have to do we don't really have to solve anything, no, that is differential equations or Bessel function. So we can approximate a solution instead of an infinite series. We can truncate. No, I hope you know the truncation of numerical methods. So you can just take the first term of the infinite series and you can solve the approximate solution of your problem. Now, this is only applicable when tau or the Fourier number is greater than 0.2. Otherwise, it will be inaccurate. Again, it should be noted that the tau should be greater than 0.2 for the Fourier number for this to be accurate. So you can find the temperature of the wall using this equation. the cylinder, the sphere, and that is for any x, no? So let's say you have a given wall, no? So you want to determine, so if this is 0, this is your L. So anything in between will be x, no? So if you want to determine the temperature around this point, you can determine that. But usually we're interested only in the center and the surface. So 0 is for the center and L will be for the surface. So remember this. This is quite important. So if you simplify this, when it is at the center, when x is equal to 0, then you can evaluate this. If x is equal to 0, and also for this, if r is equal to 0, what happens is it will reduce to this uh, it will reduce to this value, no? Or this equation. So they are the same, no? Technically. And you can find, I mean, if you want to find the temperature of the surface, you can just have L over L. So this will be just 1, no? Okay? Okay, magliit na lang. Okay, okay, okay. So you have a table for finding the eigenvalue, no, the first eigenvalue and the first constant, no, the first coefficient given a byte number. For example, you've solved the byte number that if the problem is a plane wall, you can have these values for your eigenvalue, and for your area, you can substitute the values in the formula. For cylinders, for example, have this, and for sphere, you have this. Okay. So if you want to evaluate the Bessel function, so the Bessel function is only applicable for this case for the cylinders. So if you have a cylinder problem, you have to evaluate the the Bessel function of your lambda usually. So, let's say your lambda is 0.2. This will be its Bessel function. So we might have to interpolate in between the to this table if it is not accessible here. Okay. So you can also find the max heat transfer, no, around here. So basically, this has been discussed before. The maximum heat transfer is the temperature of the environment minus the initial temperature times the mass. Okay, and also the fraction of heat transfer can also be determined. So basically, initially you have a maximum heat transfer because the temperature initially is high, but as time goes by, the temperature will be closer to the surrounding temperature, so therefore the temperature difference is smaller, shorter. Then we have a fraction of the heat transfer flow. Um, we'll discuss this later when we have the problems involved. And then for the approximate solution, we can also find, sorry, some solution left. For the Fourier number, so we've not really discussed this, but we find the Fourier number, which is also tau. Also take note that this is also tau, as the ratio of the conductive flow over the heat energy stored. Okay, so I think that's it, and thank you guys for listening.